Okay, if we want to move on to something a little bit more complicated now, so here's a truss, which is a Warren truss. Warren trusses have equilateral triangles built into them like this, so all the angles are going to be 60 degrees, and all of the sides will be equal. So we're going to load this truss unevenly now. So we notice the truss is supported by a triangular pin here and a roller joint. Now we know that the roller joints always mean that the reaction at the roller joint can only be at right angles to the surface that it's on. It can't hold any lateral movement, it can't resist any lateral movement. So we'll call that RR, and it has to be in that direction. On the other hand, this is a pin joint and it can resist lateral movement. However, we note that we don't have any horizontal forces, so we don't have any angle forces, so there's no movement on this truss pushing it from side to side. So we're safe to assume that the reaction on the left is going to be vertical as well. There's no horizontal forces. Okay, does that make sense? Now, whether I make my force come and push towards the point of application, or whether I have the force pushing away, it doesn't matter. The force can be said to be acting along at any point along its line of action. But in this case, I'm making it go away, just so I can got some more space. Right, so how do we calculate what these reactions are? Because we've got loads here, we've got distances, we've got angles. How do I know what the reactions are? Well, the simplest thing is to say this is an object in equilibrium. Therefore, this is the equations of equilibrium are the sum of all the vertical forces have to equal 0, the sum of all the horizontal forces have to equal 0, and the sum of all the moments, that capital M stands for moments, they also have to be 0. So all the turning forces, which is a distance time, I should qualify that, a perpendicular distance from a pivot point times the force, that all has to equal 0 all the way around. Now if that's the case, I can easily take all the sum of the moments, and that's sigma, capital S there, Greek letter S, sigma from all the moments about, now let's find ourselves a point, we'll call it P, about P, and we'll say, just for the sake of convention, around to the right clockwise is positive. All of those moments have to be equal to 0. So all the turning forces about this point have to be 0. All the turning forces about here would have to be 0, or there, or out here. The thing is balanced, so it's moving with constant velocity, or it's at rest, and it's in equilibrium. All forces are balanced. So I'm going to do the moments, because when I take a moment about here, this RL disappears because the distance from RL to its turning point is 0, because RL is going through the turning point. So that turning force, which is a perpendicular distance multiplied by a force, there's no perpendicular distance from RL to this point, therefore that moment disappears. Then we're left with these. Now let's just going to say we're 1 unit to make things easy. Everything is 1 unit. Every one of these sides is 1 unit. So if we sum all the moments, we'll start from here. So making it about this point, the distance is 2 units. So RR, and the perpendicular distance to that point, is 2 units, and it's a positive direction because it's going in that way, around about that point. So RR times the perpendicular distance from the point times 2 units, whatever they are. Now this, we're going to have to be a minus, because about this point, this 250 is going the opposite way. It's going anti-clockwise. So minus 250 newtons. Now what's the perpendicular distance of this force from that point? Well, it can be said to be acting at anywhere along its line of action. So we trace that line of action, we come to a perpendicular distance here, and it's going to be 1.5 units. So times 1.5 units. Any other forces? Yeah, we've got this 65 Newton force. So it's still negative because it's going anti-clockwise, minus 65 newtons, multiplied by its perpendicular distance from the pivot point, and that's an easy 1 unit, and it is perpendicular because that's a perpendicular there, times 1 unit, all has to equal to 0. Okay, well that's quick calculation there. So 250 times 1.5 minus 65, well, those two things are both going to be adding to each other because they're both negative. So that's RR times 2 minus 440 newtons equals 0. Therefore, RR equals, move this across the other side, it's 440 newtons, and divide it both sides by 2 equals to 220 newtons. So now we know that this force, beg your pardon, yeah, what did I call that? I call that RL. Isn't that silly? And I call that RR. It doesn't matter. RR should be reaction on the right. It should be on this side. Doesn't matter. Okay, so RR is 220 newtons. Now, we want to calculate the force in this member and that member. Now remember how we label things from our last, we used a system called Bose notation. In Bose notation, you label every area that's separated by a member. So let's say, and I'll try and do this in red so it makes it a bit easier to see. We'll call this area A, that area B, this area C. We'll call this area D down here, that big area, E, F, and G. And that way we can label things really easy. Like this member here will be EG. This one across here will be BF. This one here will be GD. And this to my right will be ED. So we want to know what is the force in AG. So the force in AG, what is it going to be? Alright, to do that, let's isolate that joint. Let's just take a pretend cutting. Let's cut out this little section around here like I'm doing like that. And we'll redraw it here for the sake of it so you can see it. So we've got this shape here, that's 60 degrees. We've got a vertical force which we've calculated to be 220 newtons. And we have, now again, I'm going to assume that this member here is going to be compressed, which means its internal forces will be pushing towards the joint, and this one down here will be stretched, so internally it will be wanting to pull itself back in and its forces will be pushing away. So I'm assuming the bottom line, which is GD, will be in tension, and the top angled member here will be being compressed, and that's member AG, and it's going to be compression. Now when I do my calculation, if any of my resulting forces are negative, it means that I have to change the sense of my arrow. It goes the other way, and it won't be compression, it'll be tension, or it won't be tension, it'll be compression. Alright, so now we have to solve, and it's a simple process here now to solve for these. We'll just create a force polygon, which we've done before. Remember a force polygon, when all the forces are in a system that's in equilibrium, you just add all the vectors, the force vectors, head to tail, and they have to finish up where you started, with the final arrowhead pushing towards the starting point of the first vector. So there's my 220 newtons. I'm going to have a horizontal force over here, and then I've got another one at 30 degrees to the vertical. And this is AG, and this one is GD, and we have the sense. Remember, GD is going to the right, there it is to the right, and AG is going downwards to my left, so there it is going downwards, and the vectors all close. Right, so we're looking okay here now. Now it's a simple matter of doing some trigonometry. So tan of 30 degrees is going to equal to GD divided by 220 newtons, and therefore GD is going to equal to 220 newtons tan of 30 degrees. Okay, now simple calculation. Let's get the calculator out and do this. So 220, I'll clear all that. 220 times tan of 30, 127. Let's just say to three significant figures, 127 newtons. And remember, we should say that it's going to be, because it's positive, I've guessed it correctly, it's going to be in tension. So we should always say that. And to figure out what the GD is, what the internal force is in GD, then it's another, we want GD, so let's go sine of, well, let's go, we've done GD, right, let's do AG, so we'll go cos again. So cos of 30 degrees is going to equal to 220 newtons, because that's the adjacent, divided by AG, and that means that AG is going to equal to 220 newtons divided by cos of 30 degrees. Well, let's figure that one out. Do 220 divided by cos of 30, 254 newtons. And remembering our sense, we've decided that it's going to be in compression. So interestingly, the compressive forces are much higher than the tensile forces required in this particular loading configuration. So we've said that AG has a force of 254 newtons in compression, whereas GD was 127 newtons in tension. Okay. Now we could then, using that, knowing this, we can then grab this corner here, knowing that force. We could then set up the same process, add these vectors together, knowing the angles, and then we could work out what GF is and BF. And we can just work our way through the whole structure, figuring out what each of the loads would be. And they would change, they would be different, because remember, we've got an unequal load here. The load is set off to one side, it's not loaded here, so we expect the forces here to be less than they would be on the left hand side. And so yeah, so that's the process of using the method of joints to calculate internal forces in truss members. I trust you enjoy it.